Hello, PChem students. The point of this video is to guide you through this spectroscopy project, which I am assigning you. The point of this project is to see how quantum mechanics, which is something that is maybe hard or scary, and we don't really have enough time to cover it in this course, is linked to spectroscopy, which is basically what it is to do chemistry, right? We're used to using spectroscopy to tell us we have this bond or this molecule or whatnot. And the only reason it works is because of quantum mechanics. We're going to focus in this project on diatomic molecules because they are more straightforward. So it's a little bit easier to see the relationship between the quantum mechanics and the spectroscopy. In reality, chemists have measured spectra. So you take a molecule, you measure it, and you use that to get the fundamental constants of the molecule. We're going to do that backwards since we don't have a lab in this class. So we're going to look up the fundamental constants of a molecule and use that to get an idea of what the spectra should be. And if we were to take the spectra in lab, we get basically the same thing. All right, to start the project, you have to pick a diatomic molecule, and you can choose any diatomic molecule for which you can find constants. I'm going to pick carbon monoxide, so that's, I guess, one that's off the list here. So you can go to this NIST webbook, and what you can do is search, and you can either search by name or you can search by formula. So I'm going to search by formula. I want to do carbon monoxide. I'll search CO, and it brings up carbon monoxide. Again, you can do any diatomic molecule that you like. And then what we're going to do is there's a whole bunch of data you could find for this molecule. We're going to go to constants of diatomic molecules, and we'll bring this up, and it tells us what all of these various constants mean. What we want is the ground state. So we want to go down to the bottom of the table to find the ground state of the molecule, and ground states are labeled with a capital X. So we're just going to scroll all the way down until we get to the bottom of the table. We see this capital X. We see this 1 sigma, which is the ground state for most, but not all diatomic molecules. And we can go from here. So these are all the constants that we're going to be working with, or most of them. And all of these constants have a little E subscript. That E is for equilibrium. So it's the equilibrium, bond length, what have you. I've left that out in the rest of my talk. So I'm typing these numbers in the handout. I don't have those things, just for a little bit of simplicity here. So this first constant, this capital T, is the minimum electronic energy, which will say how high an excited state is above the ground state. So for our ground X state here, obviously it is 0 above the ground state. The next constant, omega, is the vibrational constant. This constant comes from using the harmonic oscillator model, which is a good approximation for bond vibration. So think of a slinky oscillating back and forth or some other spring. That's a pretty good way to imagine bonds, but of course, bonds break in ways that slinkies or springs don't break. The next constant here, the omega x here, is the anharmonicity constant that we're going to use to modify the vibrational constant. So we're going to say, well, this comes from the harmonic oscillator. That's not perfect. We can use this term to make it perfect. This omega y is also the same thing. Some of your molecules may have this, and maybe even an omega z. We're not interested in those. We're just going to stick with the first anharmonicity constant here. The next constant that concerns us is B. This constant is the rotational constant. It does a similar thing to the vibrational constant. It comes from the rigid rotor model and describes how molecules rotate. For our simple diatomic molecules, we're just going to have one of these. More complicated molecules would have more rotation constants and vibrational constants as well. And that's beyond what we're doing here in this project. The last two constants here that we're going to use is this alpha constant and this D constant. So alpha is the rotational vibrational coupling constant, and D is the centrifugal distortion constant. So both of these constants deal with how there's a coupling between rotation and vibration. So as you have a molecule rotating, that's going to spin that bond, that's going to stretch that bond, it's going to affect the bond length, it's going to affect the vibration, and so forth. All right, so from these constants, so from T, omega, omega x, B, alpha, and D, we are going to be able to calculate some meaningful constants about the bond. The first thing we're going to calculate is the bond length. Now, note that this is the bond length here, right? So this R is the equilibrium bond length. We're not going to just read this number. We're going to calculate it, and we should get something that's pretty similar to this number. And we're going to calculate it with the equation that I provided for you. So the equation that we can use is this one here. This tells us that the bond length R is equal to the square root of Planck's constant divided by 8 pi squared times this mu thing times c, the speed of light, times b, which is the rotational constant. So what we can do is just simply plug in these numbers and calculate them. So what we need to do first is understand what mu is. Maybe you remember this from physics, but mu is the reduced mass. So when you have two objects moving in relationship to each other, in this case, my carbon atom and my oxygen atom, it's often simpler to come up with this reduced mass, which kind of combines them together and treats it as if we have one object moving from the center of mass rather than two moving objects. And that is a simple equation here, m1, m2 divided by m1 plus m2. And you could do these calculations any way you want. I'm going to do them with Excel. Calculators work fine too, of course. So let's hop in here. I have the Planck's constant and the speed of light built in. And now to make the units work out here, the speed of light should be in centimeters per second. And that's because all of our vibrational constants, rotational constants, and so forth are in units of inverse centimeters. So that's going to make the units work out pretty well here. Now, in these two cells, I have the mass of a carbon atom and the mass of an oxygen atom. This is something that you could look up if you Google search, what's the mass of a carbon atom, but it's actually pretty easy to calculate as well. So to get this, what you do is you take the mass of carbon in grams per mole and then divide it by Avogadro's number, which would give you the mass of a carbon atom in grams, and then divide it by 1,000 to give you the mass of a carbon atom in kilograms. So if you ever want to know the mass of an atom or a molecule, you take the molar mass and divide it by 1,000 times Avogadro's number, and that's going to give you the mass in kilograms. All right, so then to get the reduced mass, we simply take m1 times m2 and divide that by m1 plus m2. And that will give us our reduced mass in kilograms. And then to get R, we go ahead and plug these numbers in here. If you're not good at Excel, again, you can use this with a calculator, although it is helpful to have some Excel skills. So if we want, we can take the square root of our Planck's constant, and then we can divide that by 8 times pi. To do pi in Excel, you just type in pi, but then you have to do a open and close parentheses because I don't know, that's how Excel syntax works. Then we can square it, multiply that by the reduced mass, multiply that by the speed of light in centimeters per second, and then our B constant. And if we hop back to the website, we can see that our B constant is 1.931. So I'll go ahead and use that. So we'll go 1.931, and that'll be good to go. So here we're giving our bond length. It's giving us 1.128. If we go through and check our units, which is always good to do, those units are in meters. What I'm going to do is multiply this by 10 to the 10, and now I'll put the bond in angstroms, which is something that's a little bit more convenient to talk about bonds, because now we can say it's 1.128 instead of 1.128 times 10 to the minus 10. And if we go back and check, we see that that's actually really good. We've got the same bond length that we're getting here from the website. So that's reassuring. All right. Another thing we can do is we can calculate the spring constant. So you might remember the spring constant from physics. This describes the stiffness of a bond. Again, this is pretty easy. It's just a plug and chug here. So the spring constant in units of newtons per meter, we can simply take the reduced mass mu and multiply that by 2 pi times the speed of light times the omega constant, so that vibrational frequency squared. And that will give us the spring constant. The last thing we'll calculate is the vibrational well depth, as well as the dissociation energy of the bond, and that's these two equations here. So the vibrational well depth characterizes basically how many vibrational states we can get, how stable is this bond, and that's simply equal to omega squared divided by 4 omega x. And remember, omega x is one constant. So there's an omega constant there's an omega x constant. Again, just a simple plug and chug. You plug in those numbers, you get the answer. And then to turn the well depth, which is this, into a dissociation energy, we need to subtract the 0 point energy. So this is something we'll talk about in class, but vibrating molecules have a 0 point energy, which means they have energy associated with them. And so we simply take this energy and subtract the vibrational constant divided by 2, and that gives us the dissociation energy. So if we wanted to know how much energy we would need to put in to actually break this bond, that's what it is. It's not the same as the well depth, but it's pretty close to the well depth. So if we look at the answers here, this up top is numbers that I just looked up from the website, and these are the numbers that I calculated. So again, my bond length was pretty much the same as the website, which is great. I get my my force constant for the spring in terms of newtons per meter, and I get my two dissociation energies. And you can see that they're basically the same here. So we'll do this for the ground state, and you'll do this for an excited state as well. So all the math is exactly the same for the excited state as compared to the ground state. You just use the excited state numbers rather than the ground state numbers. And we can look at some excited states here, and we can talk about this a little bit. It's a little bit beyond the scope of what we want to do. But this X state is the ground state, and then every other state here is an example of an excited state. What I would recommend you pick is one with a capital letter. So the lowercase letters represent a different spin state. So you can see this 3 here as compared to this 1 here. The lowercase letters represent different spin states, and we can't actually easily transition between the ground state, which is called the singlet state, to this excited triplet state. Uppercase letters represent other singlet states. Again, we might not actually be able to spectroscopically transition between the ground state and every single state with a capital letter, but we definitely can't do it with the lowercase ones. Just pick one of these, and this will give you a different a state to compare to. So I picked this A state here. You don't have to pick this. It's a A state. You can pick really any state that you want for your molecule. I would pick one closer to the bottom. It's going to make a little bit more sense. So we have the same data up here. We have the same numbers. And then we also have, transitions that are possible between the states. So that's helpful there. And with this, we can go ahead and just kind of repeat our calculations. The next thing we're going to want to do is plot the vibrational energy well for both states. And so there's an equation for this. I'll go back to the sheet here. And the equation for this looks maybe a little bit scary. Here's our equation. And this gives us the bond potential. Now, you kind of intuitively should know what this looks like. I'll go through the process. We'll see what it looks like. Hopefully, if you're thinking of how would I break a bond, what does the energy of a bond look like, you come up with something that looks pretty much like this. And it's a relatively simple equation. It's epsilon. So this is our epsilon from here, our bond energy. And then we have 1 minus e to the minus a x minus r squared plus t. So we have a couple of constants here. This t, remember, is the energy we are above the ground state. So for the ground state, it's 0. For the excited state, it's the number we'll look up. And then we have this a constant, which represents, again, how easy it is to move this spring. So this isn't alpha, but it's related to alpha here. And to actually calculate it, it's the square root of the spring constant k divided by 2 times Planck's constant times the speed of light in centimeters per second times the epsilon here, e. And then we have a 10 to the minus 10 to do a unit conversion, because if we don't have this, we'll be in meters. You could plot it in meters, but I think it makes a little bit more sense to plot it in angstroms. That just gives us between 0 and 10 rather than 0 and 10 to the minus 9. So the way we can plot this is just by simply using Excel. If you've never plotted a curve in Excel, it's a little bit confusing if you've never done it before, but you have to make your own x-axis. So I'm going to make the x-axis here. And I'm going to go between 0 and 10 angstroms in intervals of 0.05 angstroms. And so to do that, we just start with the 0 point here, and then we can say I want my next point to be this plus 0.05, and that gives me 0.05. And then I can go back on this one. If I hover over the bottom right corner here and my cursor changes, and I can drag it down, and that gives me the increments that I want. So I can go ahead and make my own x-axis, and I just want to give a lot of data points. This is probably excessive, but that's okay. Excessive is always better than not enough. If you don't do enough data points, it looks a little bit janky and rugged there. And then I simply go ahead and type the equation in. So I'm going to go look up the other parameters that we need from the answer sheet, put them in here, and then we're going to go ahead and solve this. All right. So I obtained the epsilon values and the K values and the bond length for my excited state for my answer sheet. Again, we already talked about how to do all of those things, so it shouldn't be too bad. I'll calculate the A for us here. So remember, A is equal to 10 to the minus 10th times the square root of our force constant K divided by 2 times Planck's constant times the speed of light in centimeters per second, and then times our energy value here. And then we'll do the same thing for the excited state. I'll have to make some adjustments here for dividing by 0, but we can do that pretty easily. And we should have RA for the excited state. Okay, so with these values in hand, we can then go and calculate these energy wells. So all we have to do is type in the equation, being a little bit careful for our parentheses. So our energy, which is the V of x here, is going to be equal to the epsilon value. And then we'll multiply that by 1 minus E. So again, on Excel, an exponent is EXP. So that's E raised to the something that we're going to put in the parentheses here. And we'll do -1 times A times, now X minus R, what is that? So in this case, X is the bond length that we're at, which for this point would be 0. And then minus R is going to be the equilibrium bond length. So that's how we'll do X minus R. We'll close out that parentheses, and this whole thing needs to be squared. And then we'll add in T, which I have neglected to get, but for us, it's 0 for this X, so we don't have to do anything with that here. And this will give us the energy now associated with being at a bond length of 0 angstroms, which is quite high. Then what we can do is simply, we want to be able to just drag this down. Now, as I've typed it, that's not going to work for us yet. And that's because it's when we drag something down in Excel, it's going to drag every single thing down here. So if I do that, it's going to give me something weird because it's now using the constants from the excited state. And if I did it again, it's going to give me a divide by 0 error. Well, I guess it's not divided by 0 error, but it's putting in zeros for things. So it's multiplying by 0. So what we can do is come back up here and take everything that we want to not change, which is all of these constants here, and we can put a $sign in front of them. So if we go to here, O2, if we put a $sign next to the 2, that 2 won't change. And then we can go and put a $sign here on L2, and we can put a $sign on M2, and now those things won't change. And all that will change as I scroll down here is A. So it'll go from A2 to A3 to A4, which is exactly what we want because that's our X part of the vector. So we can go ahead, drag this all the way down to the bottom, and that is going to give us our curve. Let's go ahead and plot this. So we'll make a plot of this. Now, students often just do default, which is points, which is not very good looking because we actually have lots of data points. So it's much better to do a line here. We get something that looks like this. This is a little bit wonky, and that's because our focus in this plot is not on the potential energy well. So we're going to tune the axes here, and we're going to basically drop our y-axis. So instead of going to 1.6 times 10 to the 7th as our maximum, we're going to go to 100,000 inverse centimeters. And that's going to focus on the potential energy well. And so I said at the beginning that hopefully you would kind of expect to know what this plot would look like. And this is hopefully what you should see. So here, as we try to push atoms closer together than their equilibrium bond length, they repel that, they resist it, and the energy would skyrocket. At the minimum here, we have the equilibrium bond length. And then as we increase in bond length, again, the bond resists that, the atoms like to be together, but eventually the bond breaks, and we just have this no association here. All right, let's pretty this up a little bit. And then we can change the x-axis as well. We don't need to go all the way to 10 or 12, I guess. Let's go to, what does it look like if we go to 10? Looks a little bit better. We'll stop there at 10. All right, I went back and grabbed the t value for my excited state, and I'm ready to calculate the same data for the excited state. So we'll go ahead and we'll do the same thing, but we're using the numbers appropriate for the excited state. So we'll go for our epsilon, and we'll multiply that by 1 minus exp to the minus 1 times our new a value times x minus our new equilibrium bond length squared. And then we will add t. We actually have a t this time to add, so that'll give us our new energy there. We'll go back in, we'll put all the dollar signs in the appropriate places, which is everywhere except for A. And then we can drag this down and get our curve for the excited state. Let's bring the excited state into this data. There we go. So here we have our data, and we can see the difference between the ground state and the X state and the excited state and the A state. For the actual project, I'm going to want you to pretty up this graph a little bit. Let's go ahead and see the example. So this is the example that I have. So I've changed the axes here as well and made it, legible, made it look a little bit nice, put labels on there. And you can do that as well. And if you have questions on how to do that efficiently in Excel, I'd be happy to answer those. I also want you to calculate a couple of things, as you can see here, the excitation energy to excite from the ground state to this excited state, as well as the ionization energy. Now, we actually already have all the information we need to figure out what wavelength of light we would need to use to ionize the ground state. And that is this number here. So this number is the energy that comes from the not being in the ground state, but again, we're a little bit higher than the bottom of the well. And so to convert this into a wavelength, all you do is invert it. If you invert this number, it's going to give you a number in centimeters. That's a distance, that's a wavelength. And then you can convert that by nanometers simply by multiplying by 10 to the 7th. So how do we get the excitation energy? Well, that's just the difference in energy between a molecule sitting in the ground state here and a molecule sitting in the excited state here. And so to calculate that, all you need to do is take this T, and this is TA for the excited state. Again, if you used a different state, it wouldn't be A, but whatever the state is. And you take that energy, you add in the energy of the molecule in the ground vibrational state for the A state, and you subtract the one for the X state. And that's going to give you the energy of that process. Again, invert it, and then multiply by 10 to the 7th to convert into nanometers, and that will give you the wavelength of light in nanometers that we would use to excite that transition. All right, so we are now done with the UV vis spectrum and the first 6 steps here of the project. The last 4 are all that's left to do, and we're going to go ahead and do those now. These have to do with the IR spectrum of the molecule. The basic principle behind this is that molecules must excite their vibration and rotational levels simultaneously. Diatomic molecules tend to start in their vibrational ground state, but could be in any one of many rotational excited states. When molecules absorb IR light, they absorb 1 quantum of vibrational energy and could either gain or lose 1 quantum of rotational energy. To do this, one of the first things we need to do is figure out how many rotational levels are accessed. And to do this, we're going to use the Boltzmann distribution. We can calculate the probability of a molecule occupying the rotational level J using this equation here. And so this first part looks scary. Hopefully this looks a little bit easier. We can simply take this equation, do a plug and chug, and estimate the population of a molecule being in that state. And so what we have here, G is the degeneracy. So the degeneracy of the state says how many energy levels are there at that state. The more energy levels a certain state has, the more likely a molecule is in one of those energy levels. And then we take E, we raise it to the minus energy of that level, and divide by KT. QR is the rotational partition function. And for most molecules, we can estimate it using this equation here. If you have a really small molecule, like diatomic hydrogen, that's not going to work as well. And if you really want to pick that, you can be happy to give you a more accurate equation to use for that. But here we're going to use this approximation for most of your molecules out there. So what we can do is simply evaluate these things. So let's go back into Excel and work on the IR spectrum. So I have all the numbers that we have taken here. The degeneracy is simply 2J plus 1. So we can calculate that really easily. So I have a couple of different states here. And you may not get a molecule this big. The smaller atoms you pick, so especially if you have something with hydrogen, you're not going to get as many states as this. But for carbon monoxide, we have a lot of states access. So we can go in here and we can say that the degeneracy is going to be equal to 2 times J plus 1. And we could do this math in our heads too, but it's easier to use Excel. We have all the different degeneracies here. Now, what's the energy of that state? We have this equation as well. So the energy in terms of rotation for one of these states is simply this energy here. So here is our equation that we can use to get the energy of a rotating molecule. The subscripts J and N refer to the rotational state and the vibrational state. Right now, we're going to be considering only the vibrational ground state. We'll talk in a second about what happens if it's an excited state. So all we have to do to this is simply we can plug in the numbers and get the answers here. So when we have a vibrational state associated with rotation, that actually affects our B. So we can't just use the B we've been looking up, but we have to alter that to get a ground state B constant. And we can use this equation up here. So we simply take the actual B constant that we looked up, we subtract alpha times N, which in this case is 0, plus 1/2. So we can do that in Excel. If we want to do that, we'll go ahead and say that this is equal to our B constant minus alpha times 0 plus 1/2, or divided by 2. And this is our modified B constant. In the future, we're going to want this one as well. So I'll go ahead and know what I'm doing here, and I'll just subtract our 1.5 times alpha. And that's going to be used in the future here in a couple minutes. All right, so we have our new B, we have our D, and we can simply go ahead and plug in numbers here. All right, so for the energy, we'll go ahead and use the equation. So the energy of one of these states is equal to our B. So we have our new B here. And then to this, we're going to multiply that by J, and then times J plus 1. And then to this, we are going to subtract the D constant times J squared times J plus 1 squared. And so that's going to be 0 for the ground state. It's always going to be 0 for the ground state. And we can go ahead and put in our appropriate dollar signs and then drag this down here. So we want the A2 to be changing. So we'll get dollar sign. That should be good, our two constants. And we can drag this down and get the energies associated with all of these levels. Now that we have the energies, we need to know the partition function Q. So the equation for the partition function Q is provided for us here. And that is KT over sigma B. So for this, we're just going to use the constant B that we've been using, the one that we looked up. K is Boltzmann's constant, and T is the temperature. We're going to use room temperature, so 298.15 or Kelvin. Sigma is a symmetry factor. So for us doing this project, sigma is either going to be 1 or 2. It's 1 if your molecule is a heteronuclear molecule, which carbon monoxide is. So for carbon monoxide CO, it's going to be 1. If you choose a diatomic molecule, the sigma is going to be 2. And this represents, if you rotate it 180 degrees, is it the same as it was before? So for homonuclear molecules, it is the same, so you put a 2 there. And for heteronuclear, it's not the same, so it's a 1. So we'll come in here, we'll put a 1. And then we can calculate our QR here. And so I'm going to cheat a little bit and not actually calculate KT. I'm going to do 207.22. This is what KT is in inverse centimeters. So you can do that calculation in Excel, or if you taught PChem for 6 years like I have, you can just know it. And so we'll take that, we'll divide it by sigma, which again, it could be 2. For me, it's 1. And then we'll divide that also by B. And this gives us our rotational partition function. So then to calculate the probability, we simply come in here and we use the equation. So we're going to say that our probability of being at a given state is equal to the degeneracy. And then we are going to multiply that degeneracy by E raised to the negative energy level. And I do -1 times because I'm not sure what Excel knows in terms of syntax, but we'll take -1 times 0. And then we'll divide that by KT. Again, KT in inverse centimeters is 207.22, so you can just put that in there. And then we will take this and we will divide this by the rotational partition function Q. And that's going to give us a probability of being in rotational state 0. We don't want to change this Q, so we'll go ahead and put our $sign in there, but we do want to change B and C. And so then we can take this, bring it all down here, and get the probability of being at any state. So here, what we're going to do is see that it should add up to 1. We should have 100% probability. So this column here is the sum of all of my values here. So since that's pretty near 1, that's a really good indication that I haven't messed up. If you got like 1.5, you messed up somewhere. And what we're going to want to do is consider all of these states that have a significant population, which is going to be about 0.01. So I'm definitely going to include this first state, but I'm going to stop at 19 and I'm not going to include 20. Of course, there are some molecules occupying rotational state 20, 21, 22, and so on. But we got to stop somewhere, and we're going to stop there. So if the number is lower than 0.01 probability, so lower than a 1% chance of being at that state, we don't need to include it. Again, different molecules are going to have different numbers of states. I think carbon monoxide is probably one of the bigger ones, so hopefully yours has less than this. If yours has more than this, maybe pick a new molecule, or go ahead and just muscle through it. Before we get into actually calculating this spectrum here, one of the other things I want you to do is understand a little bit about the vibrational states. So we're going to calculate the harmonic energy using the harmonic oscillator potential, a more accurate anharmonic, and then try to figure out how many states are actually possible for your molecule to have. And I'm going to have you report on the states from between 0 and 5, so the lowest 6 states, although again, it can keep going up and up and up. So how do we do this? Well, quite simply, let's go ahead and get a 0 through 5 here. What we need to do is just use a couple of equations. And these equations are given to us in the handout as well. So the equation to get an energy for a vibrating molecule is this equation here. So this one is the simple harmonic oscillator approximation. And if we include this term here, we get into the anharmonic term. So all we have to do is calculate these values, and then we'll get the energies. So what you can note is that for the harmonic oscillator approximation, right, omega is a constant. And so as n increases, we simply increase omega. So we're always increasing the energy, and it goes on forever. That's not realistic because eventually we're going to vibrate the molecule so hard that we break the bond. And that's what the anharmonic term gets us. So we can go into our Excel document and go ahead and type out these equations. So for a harmonic, and then we'll do anharmonic, and we can go ahead and type in the various equations. So the harmonic oscillator approximation is omega times n plus 1/2, 0.5. And that's it. What have I done? Aha. I have to put times. So this is the energy for the harmonic oscillator approximation. And then for the anharmonic oscillator, we can simply copy this because it starts the same. So we'll copy it, we'll paste it, and then what we want to do is subtract our omega pi here, and then we will go and do our n plus 0.5 squared. And I forgot the times again. So don't forget the times. You're going to get all sorts of Excel errors. And then I'll make a difference between them just to see what's happening over time. And of course, I am asking you this as well. So the difference is just going to be this guy minus this guy. We want our A28 to stay the same. And we want our B28 to stay the same as well. And then we can drag all these down and see what changes. So as we get to higher and higher levels, we can see that the anharmonic number actually gets very different and starts to get very off from the harmonic oscillator. So the harmonic oscillator is usually thought of as being a pretty good approximation for transitions between the ground state and the first excited state. But as you get further and further away from that, it becomes a worse and worse approximation because the bond in a harmonic oscillator never breaks. To estimate the total number of vibrational states, we simply need to see where our equations here break reality. And what I mean by breaking reality is once the energy for the anharmonic oscillator goes down as we increase a quantum number, that doesn't make any physical sense. And so that reflects the breaking of a bond. So what we can do is just go ahead and take all of these numbers and drag them down again. And we can just start plugging in different numbers here. So we can plug in 20. And if we go to 25, we'll see that, okay, the anharmonic has still gone up, right? So 20 is allowed, 25 is allowed. We could do 45. Okay, we're still going up, right? Maybe we do 65, 85. All right, so we're still going up here. 75, we're at 88,000. Okay, that's good. We go to 85, 88. So something has changed here. So as for 75, we were at 88,006. And at 85, we're at 88,291. So we have increased. What does 86 look like? It's going down, right? So somewhere in between 75 and 85, we have started to go down. So we just kind of backtrack it a little bit here. So we'll go, let's go 84. That's still higher. 83 is higher. 82, 8, 485. 81, 496. 80 is 481. Okay, so 80. So as we go from 79, we're at 88,439. 80, we're at 88,481. 81, we're at 496. And then 82, we're at 485. So as we go from 80 to 81, we increase, but from 81 to 82, we decrease, which indicates that 81 here is our last state. So basically what we're saying is that the vibrational state for the 81st vibrational state is right here at the top of this well. And so we can't actually increase it anymore. There's no more vibrational states. We get dissociation at that point. All right, so that's how we get the total number of vibrational states. There's other ways that we could approximate that too. That's how I want you to do it. So all we have left to do now is to actually find the energies of the IR transition, which is going to be some amount of vibration plus some amount of rotation. And so to do that, we have to fill in the rest of this table here. So we're just going to use the J1s and the E1 plus and E1 minus, the J2 and the E2. That's for if we wanted to calculate an overtone spectrum, which we don't want to do. So we'll just focus on the ones here. And to do this, again, pretty straightforward. We just calculate the energy. So this EJ1 is the same as this EJ0. So we can even just copy this, except for what we're doing here is this is going to be the energy associated with the first vibrational excited state. So instead of using B0, we're going to want to use B1. And that's the only difference here. And these energies are going to be basically the same, although they will be slightly different. So again, you can see 3.84, 3.880, and then at the end we have 729 and 722. So they're very similar. They are slightly different. This gives important and meaningful differences to our spectra. And then what we're going to do is simply calculate the transitions. So the transitions that we're going to have, if we start with a molecule, let's say in the ground vibrational state and the ground rotational state, this molecule can excite to the first excited rotational state and the first excited vibrational state. That's the options that it can do. Now, if we had a molecule that was in the ground vibrational state and the first rotational state, this molecule could excite to the first excited vibrational state, and it could also excite in terms of rotation, but it could also go down. These are the options that we have. And so we actually have to have two branches called the P branch and the R branch of these spectra, respectively. And so what we're going to do is calculate the energy for the rotational transition. And so what that is we simply need to take the molecule in the state that it is, right? And then figure out what the transition to the state that it will be. So here I have this E1 plus, and that's meant to be the ones that go from one energy to a higher energy. So for example, if we start in the ground rotational state, we will excite to the state 1 above it. And so to calculate that, what I'm going to do is simply take the excited state energy, right? And again, we're in the excited vibrational state, so I use this one, and I subtract this number here. And that gives me the difference between them. So in other words, to excite this rotational transition, it takes 3.8 inverse centimeters of energy. And at this point, I can just drag it down here, and we'll get all the different ones. That means I'm off. But we can see here that this one is due to 798 minus 729. Now for the minus branch here, the minus branch is going to be, well, what if I start at 1 and go down? So I can't start at 0 and go down, so I'll start here at 1 and go down. And that's simply going to be equal to starting at 1 and going down. So we lose energy as we start at 1 and go down. So we started here at 3.84, and then we went down to 0. And so we can just, again, drag this down here, get all of these various energies. So all of these energies, again, you can see that they're close, but slightly different. And as we get really large, it actually becomes apparent. So 3.80 and 3.84 maybe are basically the same, but 69 and 83 are not the same. These are the rotational energies. And if I want to know how this is going to relate to an IR spectrum, all I have to do, it's really just as easy as adding these onto the vibrational energy. And I calculated that here, this 1081. Yeah, and so I take this energy and I add these numbers to it, and those are the energies that are going to be involved in any transition that I can imagine. So to actually calculate the energies involved in a transition, we need a couple of things. So these are all the energies for the rotational transitions. For the vibration, we're going from this state here to this state here. So we have to come in and we will take this number and we'll subtract this number. And this gives us our basic vibrational transition. And then to this, we will add all of the rotational transitions. So this number represents the actual transition that could be involved. And in particular, this one here is the transition from the ground vibrational state and ground rotational state into the first excited of each. And then as we drag this down, we see what transitions would be involved in all of the other various rotational excited states. And we can continue that as well. So if we just come over here, we can also get the rest of these ones here. So now we have all of these states that are involved in these transitions. Now, to actually make this look good, it's a little bit tedious, but I want you to do it anyways. I think it's good Excel skills to build here. The way I would have you do it, there's probably other ways, is to arrange all of this data from lowest to highest. And so what you can see here is that we have it kind of backwards. So this one is lowest from highest, but this one's actually highest to lowest. So we have to rearrange this to get it from lowest to highest here. And that is the tedious part, but it's, you know, it is what it is. It actually gets worse than this. So we're going to go ahead and rearrange this. And then what we're going to do is we're going to want to put Y values to it. So these are the transitions. These are the energies that would be absorbed But we want to know how much light is going to be absorbed at these various energy levels. And it's actually relatively easy. We've already done it, right? So how much light is going to be absorbed at any one of these energy levels? Well, let's go ahead and consider the one I'm moving right now. So this 2139, how much light is going to be evolved in this absorption? Well, what does it depend on? It depends on how many molecules are at this state. So this one represents molecules being in the first excited state, right, going to the ground state, as this calculation here tells us. So what's the proportion of molecules in that first excited state? It's this number here. So we can copy this, paste it in here, and that's going to give us the proportion of molecules that were at this energy level. And then this transition, of course, is due to the molecules being in excited state number 2. How many molecules are there? Well, this is the number that tells us how many molecules are in excited state number 2. And so you can go ahead and piece all of these things together, which will give us a relatively symmetrical graph here. All right. I have gone ahead and skipped through some of the steps here because, again, they're tedious and repetitive, but I'll explain what I did. And I have the data that we're going to want to plot. So first, I'll just go ahead and plot this. Again, we have a lot of points here, so we're going to want to plot it as a line. And look at this data. This is exactly what an IR spectrum would look like. We see that we have peaks. The peaks get closer together as we get to higher energies and further apart as we get to lower energies. Again, this will be more apparent depending on your molecule, but this is a beautiful looking spectrum. How did I get this? Well, again, a tedious process. So what I have here is the data that I actually plotted. And so what we have is the data points here. So again, we have our 2064.214 and the probability associated with that. I multiplied the number by 100. You don't have to. You could just use the raw probability numbers there. It would just, the axis scale would be different. And then I have all the data points that's shown here. So this is 19 to 18, 18 to 17, 17 to 16, and so forth. In between those, I went and took the average of them. So this 266.446 is the average of these two numbers added together to get a point exactly in between them. And I set that to 0 because light is not absorbed at this intensity. And so when I did that, I went ahead and got a peak and then dropping off on either side. And that's how I generated this data. At the end, I kind of just like added 3 because it looked like they were 3 apart, and a similar thing up here. I just added, 1-ish, 1.5 because they're about 1.5 apart. In the middle, we have something a little bit interesting. So in the middle, this number here is actually the fundamental vibrational transition, and that's not allowed either. We don't see that at all. And so that's set to 0. So I took some points on either side so we can just get a little bit of a bigger margin here. So this one is the 1 to 0. This is the 0 to 1. This is the fundamental vibrational only transition without rotation. And then I took the average of these two numbers here to get 3 zeros in a row. So putting those things all together, I was able to generate a spectrum that looks like this, which is the rotational vibrational spectrum. Putting all of those things together, we get a data sheet that looks like this. We have all of the information that I wanted, all put together nicely. I would like it if it was as closely formatted to this as possible. And this will just put all the things together. We get some real vibrational stuff, we get some electronic stuff, to get information about how spectroscopy is, again, fundamentally related only to these numbers here that we looked up. So we only knew things like the vibrational constant, the rotational constant, and these distortion constants. And with that, we were able to figure out what the spectrum should look like. So I went on to the NIST to get an example for the carbon monoxide IR spectrum, and this is what we see. This spectrum has none of the resolution that we had for making up numbers and doing it on Excel, but you can see the position of this is basically exactly the same as what we calculated in Excel. So we see a well here at about 2150. Again, we can compare that to our Excel data where our well is just shy of 2150, and then we see big wings going up and down, and they're basically gone by about 2060, or let's say a little bit over 2200. And if we go back and compare this to the data, again, we're a little over 2200, 2050. So this is a really reliable way to get data. And again, in reality, the data that we have comes from spectra like this, whereas we're doing it in a little bit of a backwards way. I hope this is helpful. Let me know if you have any questions, and I hope this project is edifying for you.